Hello. Okay, now that you know how to take the derivative of everything, this is our last section in chapter 3, and it is a section full of word problems. Okay, so there's no new real calculus here. This is a section of problems that are application problems to derivatives, and they are application problems that involve our friend implicit differentiation, and you will see why. So these problems are called related rates, and the key word here is rates, right? So anytime we're talking about a rate, we're talking about the rate at which something changes, but in general, we're going to be talking about time here. So the word rate is going to bring into our mind like how quickly something is happening, right? So we refer to slope as a rate of change, right? But it's how quickly y is changing compared to x. In this section, we're going to be talking about how things change with respect to time. So time always comes into these problems, and I always tell people the kind of thing that jumps out at me when I see a related rate problem are two things. One, you always see units that involve time. So you see units like feet per second, meters per second, volume units per minute, or whatever. You always see these rate units. And in these problems, as you're going to see, you are given an exorbitant amount of information. When you get a related rate problem, there's so many given values that it's almost impossible to not notice that you have a related rate question. If you don't see the word rate, which you probably will, you see lots of given information, and you see those units that are rate units, and it's usually a pretty good indication. As you can see, my favorite Powerpuff Girl here loves related rates. She's super excited. Them. Okay, so the only rate we've talked about really to date has been the rate at which y changes with x, the slope, right? So, and that's what a slope is. It is a rate, but it's a y compared to x rate. So when x changes by this much, y changes by this much. What we want to do in this section is change that, kind of flip that, and start talking about how variables change with respect to time. In other words, how quickly things are changing, because that is going to be a really important real life application type thing, how quickly something is changing. And we can look at really any quantity and how it changes over time. We're used to things like dy dt, right? That would be the distance that y is changing over time. So if we're talking about speed or velocity, dy dt would be the speed or the velocity moving up and down, right? Because it's a change in y with time. That's a change, that's a velocity or a speed. Same thing with x. If I have a dx dt, that is the change in x over time. That's a velocity. And so that's kind of easy for us to understand those. But we see other ones as well. So for example, we're going to see things like dA dt, a change in area over time. So we'll see, a surface that's growing. And as it grows, how is the area changing? Well, the area is going to change at a rate that depends, hence the word related rates, that depends on how other things are changing. Well, is it a circle? How quickly is the radius changing? Is it a triangle? How quickly is the height changing? That's going to affect how quickly the area is changing. We'll see problems. We see lots of problems with changes in volume, right? So taking it into 3 dimensions, like we'll have a tank that's filling up or a tank that's draining, and we want to know how quickly the volume of the tank is changing. So again, we have these rates. So I'm pouring water in at a certain rate, like 20 gallons per minute or whatever, but how quickly is the water level rising? That's a different rate. So there's 2 quantities that are related to each other, and everything is changing. Everything is in motion in these problems, right? There's almost nothing that's static in these problems. Every once in a while we get a nice static quantity, but there's a lot that's moving. These problems have literally moving things. We see airplanes and boats and people walking, and we see lots of tanks filling up and leaking and all kinds of good stuff. I feel like these are the types of problems that people bring up when they're making fun of math, where they're like, a train leaves this station at this time and a train leaves this station at this time. Yeah, that's these problems, right? You have a train in motion this way, you have a train in motion this way, and then they ask you a question about like how they're how they're related to each other, maybe the distance between them or something like that. Lots of things in motion and related rates. Okay, so the way we're going to do it is we're just going to do it, right? There's not really, like I said, any more calculus here. We're just going to use what we already know to get at these problems. All right, so this is a pretty classic question, and it's kind of as simple a one as I could come up with for a good start. Plus, I found this super cool. Is it a GIF? I believe it's called a GIF. Little diagram. So it says, find an equation that shows how the volume of a cone changes as its radius and height change with time. So my little GIF is not animating and it's upsetting me. Let me click it. There we go. Okay. So as you can see, the shape of this doesn't change, right? It's a cone. When it's way at the bottom and it's a tiny cone, or when it's all the way at the top and it's a big cone, it's still a cone. What's changing is two things. The height of the cone, right? As that level rises, your cone gets taller. But the other thing you got to notice is as it gets taller, it also gets bigger around. So there are three things changing here. The height of the cone is changing. The radius of the cone is changing. And as a result of those two things changing, the volume of the cone is changing. Now, we know how to relate the volume of a cone to its radius and its height in a static situation. Like if I say to you, a cone has a height of 20 feet and a radius of 6 feet, you can tell me the volume of that cone because you know the formula for the volume of a cone, right? What we want to do now with calculus is not talk about the static situation. I don't want a volume equation. I want an equation for the rate at which the volume is changing. In other words, I want an equation for the dV dt. How quickly is volume changing? So notice this says the volume of a cone changes. So I want to know how the volume of a cone changes. That's a dV dt. Okay, now I put this picture up here because I'm consistently fascinated by two things. One, nobody ever knows the volume of a cone formula. And two, I'm just flat out fascinated by this. So I don't know if you know this, but a cylinder is exactly 3 cones. So in other words, a cylinder that has the same height, notice that this cone and this cylinder have the same height, and the same radius. So the base of this cone is identical to the base of this cylinder. When that's the case, 3 of these make up this. So visually, I have a problem picturing smashing 3 of these and having it fit in there. And every year someone suggests to me that I build some out of clay and then see if I can do it. I'm not going to do that. But I thought that this was a pretty cool little diagram that shows like you dump 1 cone in and then 2 and then 3, right? So everybody knows the formula for a cylinder, right? It's pi r squared h. And if you don't know that, let me remind you that you know the formula, hopefully, for the area of a circle, right? Pi r squared. So pi r squared is just like this surface right here. If you then want the volume, all you have to do is multiply by the height. So the volume of a cylinder is your pi r squared h, and then since it's not a cylinder, since it's a cone, I'm popping a 1/3 out front. Right? So that's my formula for the volume of a cone. And I think it's so crazy that people forget that formula, but I will say this, AP is very kind about it. They will often put in parentheses, remember, the volume of a cone is, like, they don't want to insult you and just give it to you, but they're like, we'll just remind you. We know you're under a lot of stress these days. It's really nice of them. Okay, so the key to related rates, the hardest part is coming up with an equation. Once we have an equation, we know how to do implicit differentiation. We know how to take derivatives. But coming up with the equation is a kind of a new level. So when you look at a related rate problem, they're not going to give you an equation and say take the derivative. It's our job to look at the situation, figure out what our variables are, right? What's changing? It's a related rate problem. So what quantities do we have here that are related? What kind of things are changing and causing other things to change? Get those variables, make a list of them, and then go, okay, let me reach into my bank of knowledge about math and science and the world and come up with an equation that relates those variables. Okay? If I can come up with an equation that relates all of my variables, I'm halfway home. I'm taking a derivative and I'm almost done. Okay, so in this case, again, we said I need to know how the volume of a cone is changing. So I need an equation for volume, right? If you want to know what dV dt is, then you better darn well start with an equation that has a v in it. Because the only way to get a dV dt out of a derivative is if you have a v in your equation. Okay. So I can't write an equation right off the bat that has dV dt in it. I don't know what dV dt is, but I can write an equation that has volume in it. And once I take the derivative, I'll have my dV dt. Okay, now I need then the volume of a cone, right? So I know the volume of a cone. I like to think of it, so it's 1/3 pi r squared h, or some people put the pi over 3 like this, r squared h, and that's fine too. Okay, now here's the key. In the equation that you write, so you're going to say, okay, I need an equation for volume. I need to find a dV dt, so I've got to write an equation for volume. Cool. Okay, now look at your equation and say, well, what other variables are in it? I have an r in this equation, so radius. And notice it says it wants there to be radius in there. And I have an h in here. So height. Good. That's what this is asking us for, right? It says find an equation that shows the volume, how the volume changes as its radius and height change. One of the things you have to do, though, in these problems is always, always, always make sure that you have all of the information you're going to need before you get to doing calculus, because sometimes you got to get sneaky with these equations. And what I mean is this, and this is what I was saying about you get lots of information given to you. If you have a v in your equation, when you take the derivative, you're going to get a dV dt. If you have an r, you're going to end up with a dr dt. If you have an h, you're going to end up with a dH dt. So the number of variables in these equations, when you take the derivative, doubles. For every variable you have in that equation, when you take the derivative implicitly with respect to time, you're going to get not only that variable, but the rate at which that variable is changing with respect to time. So when I take the derivative here, I'm going to end up with a dV dt, a dr dt, and a dH dt. And I want that because it says how the volume changes as its radius and height change. So as the height changes, dH dt, as the radius changes, dr dt. I want that. But if we have a situation where, let's say they didn't tell us dH dt, if you don't have dH dt, you better get that h out of the equation before you take the derivative, because otherwise you're going to have an equation that you don't have enough information to finish off. Okay, so we'll talk about that more as we go through these examples. But let's take this equation. I'm going to use the pi over 3 r squared h because it's a little easier. And let's take its derivative implicitly. Okay, so the derivative of v is just 1 dV dt. Okay, so again, I'm taking the derivative with respect to time. So it's implicit. So the derivative of v with respect to time is 1 dV dt. Now over here I have a product. So I'm going to put the pi over 3 out front, and then I'll take care of my product. So I have r squared, and I need to take the derivative of h with respect to time. So the derivative of h is 1 dh dt. Okay. Plus my h, and I need to take the derivative of r squared with respect to time. So that's going to be 2r dr dt. Now look what I have here. I don't really need this one. I now can tell you how quickly the volume is changing at any instant. If you know the rate at which the height is changing and the rate at which the radius is changing. Okay, so is the height changing by a centimeter per second or a mile per minute? The faster the height is changing, the faster the volume is going to change. Same thing with r. The faster the radius is changing, the faster the volume is going to change. Is the height growing? Because if it is, the volume is going to go up. Is the height shrinking? Because if it is, the volume is going to go down. Right? So we need to pay attention to that as well. But look how this equation fleshed out. Everything still matters. I need to know at any instant what was the actual radius of the tank, what was the height of the tank, but I also need to know at what rate was the height changing and at what rate was the radius changing. All of those things together are going to tell me at what rate the volume was changing. Okay. Now, I purposely didn't put any numbers in this first one because I need to stress to you that when you do related rate problems, and I'm going to show you one here in a moment, there are a lot of numbers. Don't touch them. Do not put those numbers in the beginning. And here's why. If I had told you, oh, well, tell me the rate at which volume is changing when the radius is 10. And people tend to go, oh, okay, well, the radius is going to be 10, so let me put a 10 in right here. Well, if you do that, then when you take the derivative, you're not going to get your dr dt. It's not going to flush out. So you never, ever, 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 ever want to plug numbers in before you've done your calculus. And that is a really common thing because we think like, oh, well, let me just plug these numbers in and it'll simplify everything. Yeah, it simplifies it right out of being correct. Right? I need that r because I need a dr dt in my derivative. If you replace it with a number, you're not going to get a dr dt. I need that h because I need a dh dt in my derivative. If you replace it with a number, you're not going to get your dh dt. So you can never, ever, 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 ever plug numbers in before you do your calculus. All right, let's take a look at one that has numbers. I censored the numbers. I wanted to help you resist the temptation. Okay, so we're going to talk about a 4-step method for doing any related rate problem. Your first step, don't skip this step. This is the physics teacher in me. Make a stinking sketch. Read that problem and make a sketch of the situation. The sketch is going to help you figure out your equation. Remember, they're not giving us an equation. We got to come up with it. Okay, so we have a 25-foot ladder sliding down a wall. All right, let's draw a picture of that, right? So here I have a wall and a floor, and here's this ladder, right? And notice that, so the ladder's leaning on the wall, but it says it's sliding down a wall. So see this little arrow right here? Okay, this is to indicate that the arrow, this ladder is sliding down. And then notice a little arrow over here. Because this ladder is maintaining its length, it's not like it's shrinking or growing as it falls. It's an old-fashioned wooden ladder. Okay? It's also going to be sliding out on the bottom. So at any moment, if you took a snapshot of this situation, there would be a certain distance here, a certain height that the ladder was on the wall. They're calling that y. And there would be a certain distance out away from the wall that the base of the ladder is. They're calling that x. But also at any instant is the rate at which it's falling. Is it falling at 1 foot per second, 1 foot per minute? What's it doing? Right? And the rate at which it's moving out. Now you might be thinking, as I'm inclined to think incorrectly, wouldn't these two rates be the same? No, they're not. They are not indeed, and you will see how that flushes out in the math. Okay, so we're going to make a sketch, and when we make our sketch, we're going to label our variables, but we're also going to label our rates at which those variables are changing, and that's what those arrows are all about. Okay, so I have y, and that ladder is sliding down the wall. So this arrow is what I'm going to call dy dt, right? This is the rate at which y is changing. And it's important to notice that y is shrinking. So I like to put in parentheses, oh, by the way, this is going to be negative, right? Y is going down. Y is shrinking. So the rate of change for it is going to be negative, just like a line that has a negative slope, right? If y is going down as x grows, you have a negative slope. Y is going down over time, so we have a negative rate of change. So at any given moment, there's a certain height that the ladder is on the wall, and then there's the rate at which it's falling. We have the same thing in the x direction. We have a distance that it is away from the wall, we're calling that x. But then we have this rate at which x is changing, and that is a dx dt. Again, worth noting, and very important to note, that as y falls, x is getting bigger. So dx dt is going to be positive, right? They're not going to give you that in the problem. It's our job to know what's growing and what's shrinking. Okay? Whether my rate is a positive rate, which means an increase, or a negative rate, which means a decrease. Okay. Now, we also have this z value here, because this is the length of the ladder, and this is static, right? The length of the ladder is not changing. So we want to know, how quickly is the base of the ladder moving? That's dx dt. How quickly is the base of the ladder moving? That's dx dt. That's my big question. And it says when it is blank feet away from the wall. All right, so first question is make a sketch. All right, the next thing we do is write an equation. Okay, so look at the picture you have. What you're looking for is an equation that relates the variables that are in play here. So I need an equation that relates x. I know x has to be in the equation because I need a dx dt. Y has to be in the equation because I need a dy dt. Right? These things have to be in the equation, an x and a y. Now, there might be other stuff in the equation, but you've got to have x and y. So I need an equation that will relate x and y for me. Now, this is a pretty common one. Hopefully you see you have a right triangle here, right? So the as long as somebody built this wall square, hopefully it's not leaning, right? This is a right angle. So I can write an equation just very simply using the Pythagorean theorem. I know how x and y are related. It has to be true that x squared plus y squared equals z squared. Has to be true. There's my equation. Okay? That's how x and y are related. Now, it also happens I need z, right? So if they didn't give it to me, then hopefully they gave me enough information to figure it out. But I'm going to need z because that's how x and y are related. Okay. Next trick, we use implicit. Right, notice I'm not playing with any numbers yet. Don't touch a number until you're done with the calculus. So now I know how they're related. So let's take our derivative of this implicitly with respect to time. So I'm going to take the derivative of x squared. The derivative of x squared is 2x dx dt. I need to take the derivative of y squared. That's 2y dy dt. So I'm taking the derivative with respect to x. And then I'm going to take the derivative of z, or z squared, right? So that's going to be 2z dz dt. Again, notice, look what happened. I started with 3 variables. Now I have 6. So I started with an x. I ended up having an x and a dx dt. I had a y. Now I have a y and a dy dt. I had a z. Now I have a z and a z dt. Every variable that's in your equation, when you take the derivative, it's going to pop out the rate at which that variable is changing. Right? So anytime you need to include a rate at which a variable is changing, you better darn well make sure that variable is in your initial equation. Okay. Now that we have our equation, now we can take a look at numbers. Right? Until you've done the calculus, never, ever, 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 ever look at numbers. Right? So here we go. Now's the moment when we're going to look at numbers. I will remove the blockages. Okay, so a 25-foot ladder. So look what we know. Z is 25 feet. So this, let me get a different color. Z is 25 feet. Okay, now, also worth noting, this is a 25-foot ladder. Its length isn't changing. So I also know, without them saying, what dz dt is. Z isn't changing. That ladder is staying a constant length. So my dz dt here is 0. Okay. Then they go on to say that that is sliding down a wall at a rate of 0.8 feet per second. Here's those units I was telling you about. Feet per second. That is screaming, I'm a related rate problem. Okay. This word right here, down the wall, we already noted that means it's going to be negative, right? This is my dy dt. It's sliding down the wall. This is how y is changing with t. They gave you your dy dt. Dy dt isn't just 0.8, it's negative 0.8. Okay. Feet per second, but I'm not plugging the units in. I'll do that in the end. Okay. It says how quickly is the base of the ladder moving, which we know is dx dt. So in my equation, this is my big question mark, right? When it is 10 feet away from the wall. So 10 feet away from the wall, that is your x. In other words, this is 10. So I know my x. So take a look at your equation. I could cancel these 2's out if I wanted, right? There's a 2 in every term, so I'm not even worried about this. I know my, oh, I wrote x. I should have written 10, sorry. Okay, I know my x is 10. I know my dx dt is what I'm looking for. So I want to leave dx dt in. That's what I'm looking for. That's my variable, which means everything else needs a number. Okay. Y, I don't have. dy dt they gave me. They gave me z, and the fact that z isn't changing handed me dz dt. So the problem I have right now is that I don't know why. The good news is I can find it, right? Because look what they gave me. The same idea that we started with, that I know how x and y and z are related, right? If this is 10 and this is 25, I can figure out what y is. At the exact moment that y is, or that x is 10, I need to know what y is. And I'm just going to use the Pythagorean theorem to do that, right? So y squared plus 10 squared has to equal 25 squared. So 25 squared minus 10 squared, I type 10 squared into my calculator, is 525. We take the square root of that, and we get 22.91287847, whatever. I'm going to write down 22.9, but I'm going to store that number in my calculator, right? Right now, before I do anything else, I have the number up on my screen. I'm going to store, and I'm going to store it, you know what? I'm going to store it as y, because I can, and that's what it is. So I'm going to hit alpha y. The y is above the 1 key, in case you're looking for it. Okay, so now when I do a calculation, I'll be using that full number and not a rounded number. So here I go. I have 10 times dx dt plus 22.9, also known as y in my calculator, times negative 0.8, that's key, equals 0. 25 times 0. So this is a pretty easy solve for dx dt, right? I'm going to take that 22.9, multiply it by negative 0.8. I get 10 dx dt minus 18.3, and a bunch of numbers is equal to 0, right? I'm going to move the 18.3 to the other side and then divide by 10. So I get my 18.3 divided by 10. And again, this is a longer decimal that I'm keeping in my calculator, so I'm going to divide that by 10, and I get 1.833, and that is the only answer AP is going to accept because the next digit is 0. So there is no rounding up. Okay, now, first thing I want to do is make sure that this is reasonable, right? First of all, it's positive, right? Which I said should be happening. dx dt is moving away from the wall, x is growing, this number should be positive. If this number comes out negative, that's physically impossible, which means you probably missed a negative somewhere else, so keep an eye on that. So that is reasonable in that sense. The other way that it's reasonable is that it is ballpark around the rate at which y is changing. So y is falling at a rate of 0.8. This is coming out at 1.8. If this was falling at 0.8 and this was going out at like 100, something's not right. Okay. The last thing you want to make sure that you do is get units on here. This is a rate. It's a distance over a time. So let's go back up to our problem. We were dealing with feet and we were dealing with seconds. So this is feet per second. On these questions, we very, very often have a point for units because units are a big deal here, right? It's not feet, it's feet per second. Okay, so I was going to do another example in this video, but I'm already at 32 minutes. So I'm going to shut up for now and I'll make another video with a second example. Okay. The best way to get good at related rates is to try related rates over and over and over again. So I have lots of practice for you, and we will do some together in class, and you can work on your own on them. Really popular question. All right. Give me any questions that you have, and then you can look for some more videos with more examples as well. All right. I'll see you soon.